PowerPoint. And then I'm do the screen share. There we go. We got screen share going, and it automatically reports. I have to tell you this it's kind of funny. I just came back from an academic senate meeting, and there was an election. So I just thought, we can do the technical stuff right here. I can use the form, and then I can use a spreadsheet. I can check against a roster of people who are supposed to vote. So even if other people have a link to the form, it's not going to matter. So I got the whole thing set up, tested the whole thing, and it didn't work as expected. A lot of people were having problem getting to the page or signing into the SSO, the single sign-in page of Los Rios, because they were using the regular browser. And if you use a regular browser that you use for like personal stuff, it stores a lot of cookies associated with Google Identity. And then you're trying to sign in using that browser into the Los Rios network, doesn't work. Yeah. Yep. What do they call it? That is a good question. I never really know why it's called a cookie. You're talking about the tiny little bit of data that is stored on the client side. So every time you make a request to the server side, that little piece of information is attached to the request. So the other side can maintain what we know as a session.
The term cookie was derived from an earlier programming term, magic cookie, which was a packet of data program. That kept unchanged. The packet of data that was kept unchanged even after being sent to receive special.
But why is that called magic cookie?
Yeah.
All right. Well, if we go down that rabbit hole, that can pick up the entire. So we're going to get started with this program, which I sent to the entire class as a part of the announcement of today. I'm hoping some of you at least have some time to take a quick look at it, because that's going to be the focus for today. We're translating this program into assembly language code. So we want to kind of take a look first at the C code and then find out what it does, and then we'll translate that into assembly code. So we'll do this line by line. Okay, let me turn on line numbers. There we go. So hope you guys cannot see it because for some strange reason, the screen, it's not okay, let me see if I can fix that. Say auto. Okay, there's auto. There you go. Okay, now it works. Okay. So let me move everything back to where they're supposed to be. There we go. All right, so we're going to take a look at this program. Line 3 to line 7 is the definition of a structure, which is analogous to the definition of a class. If you have only taken CISP310, you may not be introduced to the concept of a class, but you should have been introduced to the concept of a structure. Is that correct? Okay, very good. So the structure has a name. Not all structures need a name. You can basically have an anonymous structure where you only use it to stamp out one or two variables. And since it's a very local scope, it does not need a name. In this case, the structure does have a name of node, N-O-D-E, with an uppercase of C. So I'm basically using the same naming convention of C++ or object-oriented programming, where the name of a class starts with the uppercase. Is that okay so far? So node is basically describing a cookie cutter. Okay, this is the name of a cookie cutter. The cookie cutter specifies that a node has two members. It has two components. The first component is called V on line 5, and it has the type of unsigned 8-bit integer. The second member is called P next, which is pointer to next, and it has a funny type because the type of the P node is struct node pointer to. Okay, so do we have any questions about line 5 and line 6 as members of the structure node? No question? Yep.
So that structure is just like the pointers for that.
That is correct. That would be the intention of that member. So P next is intended as a pointer to the next node. This program is called LL, which is linked list. So we are trying to create a linked list using this program. In fact, the linked list is pre-created in a very static way, and we just want to kind of traverse it and put the value of each node into a particular element of the array. All right, so any other questions between line 3 and line 7? Yep.
Well, I guess the parameters for the static structures, is that?
Well, okay, wait. We're still only looking at line 3 to line 7.
Just say, is that what struct node P next? So that's the next, it's pointing to the next node in sequence.
The next node in the linked list, yes. All right, so are we good so far? All right, and by the way, this program does compile. Okay, if you want to try it out, set up some breakpoints and take a look at the static local variables and whatnot, that's totally doable. So now we're focusing on main, which is the only subroutine in this case. Main has a bunch of local variables, but not every single one is auto. Did you guys talk about auto versus static in CISP310 when they talk about local variables? Nope. Okay, not a problem. I'll explain that. All right, so we have node N3 in a local variable, N2 is a local variable, N1 is also a local variable. But unlike most local variables, these three start with static. So the question is, what does it mean when you have a local variable that is tagged static? And if it's not static, then what it is? What is it? Yes, go ahead. No, it's not the same thing as const. Yeah, static means it is not on the stack. Okay, it is not on the stack. By default, it has what we call a class, which is not to be confused with the class of in object-oriented programming. So if you don't specify your static, it is automatically auto. AUTO is assumed. There was a question. Let me get to that question first.
Isn't it like it's only as a small line?
So there are two aspects of variables that we need to think about. The first one is scope. So the scope is still the same as any local variable. In N3, it's only visible from inside main as a function. No other function can see this particular entity. So from the scope perspective, a static local variable behaves exactly the same as any local variable. Question?
If you change the static variable, you don't have to pass it by reference or change. Like outside of the function, like you can pass it to a different function or change.
The best way to describe a static is it is not on the stack. It is statically allocated, which means no matter which invocation you're dealing with, that particular local variable would remain the same. I think since we are having a little bit of a confusion about what is static, maybe I can just illustrate using a different program, so that I can show you what is static versus what is not static, which is auto. Okay, would that be okay? Okay, all right. I'm kind of surprised that they did not talk about static versus not static in CISP310 because this is a fairly important topic. All right, so I'm just writing a new program called static.c. And in this program, I have f as a subroutine. Okay, it's a void function. It has a local variable that is a static, and we'll just make it unsigned. And we'll make this x equals to 0. So a static local variable is typically initialized. In other words, you have to tell it, you have to tell the compiler, what value the static local variable should start with. It's not necessary, it's not all the time, but typically the use of a static local variable does need an initialization. And then every time we call f, we're gonna increment x by 1. That's all we do, okay? So now we have your usual main, right? And I'm just gonna call f a bunch of times, like 3 times, okay? So you look at this program and go like, that's a totally pointless program because the local variable x is not returned, it is not used in any way. All we do is to declare it starts to exist. We increment it by 1 every time we call f. That's all we do. But this program will differentiate between what is static and what is auto. Because without a static, then every single time I increment x, it will go from 0 to 1. It will go from 0 to 1 because every time you call the subroutine, it will reinitialize the local variable to 0 without the word static. With the word static, that initialization is a one-shot deal. And in addition to that, the value of the static local variable will persist across invocations of function f. Which means the first time I call f, it's going to increment x from 0 to 1. But that value of 1 of x is maintained. So the second time we call f, it will increment x from 1 to 2. And then the third time, it will increment it from 2 to 3. Okay? Now, the necessity to use a static local variable does not happen very often, but it does occur in certain cases. Okay, especially if you're dealing with multi-threaded programs where the same subroutine can be called from multiple callers, quote unquote, at the same time or interleaved in a certain way. So in those cases, a lot of times we require the use of a static local variable to track certain things. But for this particular example, we'll just go ahead and try it out and find out what it does. So gcc-d-o static.c, and then gdb static. And we'll put a breakpoint on line 6. Yeah, line 6 will be good. There we go. And then we just run the program. This is the first time we get to line 6. And if I print the value of x, what do you think I should get? We are currently on line 6, which is after the plus x. 1, okay, very good. Okay, so we confirm it is 1. And then we do a continue, which means it will continue execution until the next time we get to the same line, which is line 6. And we'll print x again. It is 2. And then we continue again, and this time it is 3, just as I described. So what this is telling you is the allocation, the storage associated with the static local variable x is not on the stack. Because if it was on the stack, then we would be pushing and popping, pushing and popping, and pushing and popping, and there's no guarantee that it would remain exactly the same across the multiple invocations. We doing okay so far with this? Yep.
If you put that in main and you increment it in the void function for the scope.
What do you mean by put what in main?
Static, the declaration is static. Period.
But main has no local variables in this case.
No, I'm saying if you declare it in main, you pass it into the void as a parameter.
Yeah.
And you increment it, but don't return it for the scope.
Oh, I see. You have to pass it by reference or by pointer, by address, and then have f to increment it. Yeah, you could do it that way.
So even if it's void, it doesn't.
Void means you cannot return
Yeah,
anything.
you're not returning anything, but it's static, so it still goes up.
In that case, would it even matter if it's static or not, since it's already
Right.
inside the namespace of the main function, so it's all the same variable all the way through anyway.
Right, you're still passing the same thing to the subroutine to increment. So whether it is static or not does not have made any difference. Right. I think you're first and then you. Go ahead.
So if it's static and it's not on the stack, then where is it at?
Sorry?
Where is it at in memory if it's not on the stack?
Well, it is just, kind of sprinkled around like global variables.
That's what I was gonna ask.
Yeah, so it's kind of like a global variable, except the scope is limited. So remember those two things, you have scope, which is, which part of the program can refer to something. And then you have the lifespan of something, which means when does it start to exist and when does it cease to exist. So in that case, the static local variable has a local scope, which means only the subroutine that contains the declaration can see it. But it has a lifespan that is comparable to any global variable. It starts to exist as soon as the program runs, and it does not cease to exist until the entire program is all done. Is that okay so far? All right. So we are going to do one more thing. Okay, so we're going to do one more thing before we go back to our regularly scheduled program, which is to change this to the other one. So if you don't say static, it is automatically assumed to be auto. So all this time in CISP 360, 400, 430, you have been using auto local variables all along. It's just that you may not have been told about the differentiation between auto versus static. Are we good so far? All right. So if I were to change the program by doing this, or simply removing the word static, which does the same thing, let's see what happens. So we compile the program, the GDB the same program, put a breakpoint on line 6, run the program. This is the first time we get to it, and I can even list line 1 to 6. Oh, list. Okay, I thought there's a way to specify the line number. Okay, maybe 4. There we go. So we are still stopping at line 6, and this time X is a auto local variable, which means it is allocated and initialized for every invocation. And it will cease to exist when the invocation is gone. In other words, as soon as F returns, the local variable X will cease to exist. Okay. So now I can say print X, it is 1, just like last time. Continue, print X, it is also 1. Print X, continue. Print X, it is also 1. So this is one main differentiation between a static local variable versus a auto local variable. Are we doing okay so far with the concept? We all good? Okay. So with that in mind, we are going back to the original program, like this one. So in this case, I really do not need to make N3, N2, and N1 static, but I choose to do this because I want to show you how this works for one. And then the number 2 thing is it's really messy if you want to create initialized auto local variables. This is a little bit easier from the implementation perspective, and that's why I chose to make these static local variables. Is that okay? So if that is okay, if the concept of static versus auto is okay, then we focus on just line 11, and then we want to find out what it does. It is N3 is a initialized local variable that is static. 67 goes to the first member, and then 0 goes to the second member. So that means when I create N3, 67 goes to the member called B, and then 0, which is the same thing as a null pointer, goes to the number that is called P next. So that's how we can create entire structures that are initialized. Is that okay so far? Any questions about this? So N2 is created pretty much the same way. 31 goes to the member B, and then the address of N3 goes to the member called P next. And then when we create N1, 78 goes to the member B, and then the address of N2 goes to the member called P next. So this way we have a linked list, okay? In other words, if I somehow get the address of N1, I can use the P next to get to N2. And once we get to N2, we can use its own P next to get to N3. When we get to N3, we take a look at the P next and go like, hey, you have a null pointer. You must be the last on this particular linked list. So that's why the null is here, because it's an indicator that N3 does not have a quote unquote next node anymore. It is the last in the linked list. Are we doing okay so far with this concept? Okay. All right. So if that is okay, we move on to line 14, which is just declaring an array of 4 unsigned 8-bit integers. Line 15 has a local variable I, which is just simply unsigned. And then line 17 has a local variable that is called Pn, and it is a pointer to a struct node. And then this is the loop here. So the loop basically says, let's do some initialization first. I is initialized to 0, because it is the index into the array. Pn, or the pointer to the node, is initialized to the address of n1, because it is my first node of the linked list. And then if I want to stay in the loop, I want Pn to be non-null, because having the null pointer means I'm already at the end of the entire linked list. And then the operation I need to do per iteration is actually broken up into 2 parts. Pn gets Pn equals to P next, means I want to update Pn to be the next node of the linked list. And then the other one is plus plus, I plus plus, which is a post increment operation. I could have put I plus plus over here and then just turn line 20 to refer to I without the plus plus. That would have achieved exactly the same. So do we have any questions about this program? What it does? Yep.
You're storing the values into the array, basically.
Yep. I'm storing the values of each node in the specific order of where they appear in the linked list into the buffer or the array, or we just occupy as many bytes as necessary. All right. So any questions? Any other questions? No other questions? All right. So if without any questions, we are going to implement this whole thing in TTP ASM. So we'll do a vertical split. So this way I can work on ll.ttp_asm. Oops. ell.ttp_asm. There we go. All right. So we got a few new concepts to talk about. The first one is how do we define a structure in assembly language program? The answer is it doesn't have any language feature to support that. So we have to use whatever is already existing in the assembler in order to kind of implement the definition of node as a struct definition. So, how are we going to do that? So to do that, maybe the first thing I need to do is to take a look at the program and let it run in C, and then you guys will get some idea of what we need to do. So we'll do a gcc-o-ll.c gdb ll, and we'll put a breakpoint on line 18. Okay, that would be fine. Okay, run the program. So now what I'm interested in, okay, let me scroll up a little bit so the people in the back can see it. There we go, scroll up, there we go. All right, so the first thing we want to do is to say, can you tell me what is N1? Okay, so N1 is not really surprising. It is 78 because that's how we initialize it. And it displays as the ASCII code of N, the 78 in decimal is indeed the ASCII code of N. And the P next is this bunch of numbers here, and it tells you that that is the address of N2. So GDB is actually pretty smart. When it looks at an address of something, it will try to see if it can recognize that address to be the address of a known variable within the scope. And if it does make a match, it will just say, hey, this is also known as the address of N2. So we good so far? So you don't have to take my words for it, because you can always say, tell me, where is N2? And it is exactly the same thing. Are we good so far? But the most important thing I want to illustrate is where is each member? So where is the member of N1.b? Where is member B of N1? Okay, it's somewhere. And then we can ask where is the member P next? Okay, so you can see that these two are related. This address, the address of P next as a member is after the address of B, which is also, which is the first member. So there's one more thing that is important. Where do you think N1 is? I'll let you guys guess for a moment. You just have to think about this as, if the compiler is reasonable, where would it put N1? Knowing that B as the first member is at location blah, 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 2, 0. The next byte, okay? The previous byte, the next byte. Any other guesses?
The same byte.
The same byte. All right, we'll check it out, right? We'll check it out. And it is the same byte. In other words, the address of the first member of a structure is at the address of the entire structure itself. Does that make sense? Okay. Now, the next question that some of you probably will be asking is, but V is just 1 byte. How come it takes 8 bytes to get the P next? How come it is off by 8 bytes? So the answer is a little bit complex in this case, because it has to do with the Intel architecture is byte addressable. Okay, in other words, every address is identifying a unique byte within the memory space. That's why it's called byte addressable. But the organization of the bytes is a little bit different physically. So when you buy RAM components, or they're called DIMMs, dual inline memory module, the width of the data bus is actually really wide because it's a 64-bit architecture. So the width of the data bus is at least 64 bits, which means every time you read from memory, it is reading in 8 bytes at the same time. Are we good so far with that idea? Okay. So every time you read, it is reading in 8 bytes. So without this plus 8 here, instead we're trying to save as much memory space as possible. Instead, it is a plus 1. Now we have a problem. The problem is the next read, we will have to break up. Reading the P next member now needs 2 operations. The first operation will read the first 7 bytes out of P next because an address will take up 8 bytes. And then the next one will read only the last byte that is the last part of P next. So it is not efficient in terms of runtime efficiency, even though you gain storage efficiency. So instead of and generally speaking, the compiler will sacrifice space to make it run faster. You can turn in the switch and tell the compiler, I can save as much RAM as possible, but it's okay to run slower. So in those cases, this plus 8 will become a plus 1. In other words, we'll make the structure use as few bytes as possible. Are we still doing okay so far? All right, maybe. Okay, what about this? I would say, what is the size of a struct node? Okay, I will not press the enter key just yet. I will let you guys think about this for a moment, and then I'll press the enter. Yep.
So in the same struct, everything would be 8 bytes away for performance reasons because we go from 8020 to 8028.
Yep.
But then the next struct N2 isn't 8 away from that, it's only 2 away at 8030.
No, but remember those are hexadecimal digits.
Oh, right, okay, yeah. Yep.
So between the 28 and the 30, there are 8
That's
bytes.
8, okay.
Yep, so there are 8 bytes in between.
Gotcha.
Okay, so given what we have seen so far, even if you don't understand within the structure how things are organized, what do you think is the size of one struct node? Just by looking at the addresses of N1 versus the address of N2.
16 bits.
16 bytes, okay, 16 bytes. Yes. So it does, each struct node takes up 16 bytes, of which 7 is really not necessary, but in order to optimize for speed, we, make it 16 bytes instead of 9 bytes. Are we doing okay so far with this, picture? Okay. So now, when we are going to translate this code into assembly code, we have to make some adjustments, okay? Because we have to make the adjustment of, we are dealing with an, oh, okay, I forgot that I put it somewhere else already. So we quit this one, go back to this one, there we go. All right, so in TTP ASM, the way we define the structure is only using labels, okay? So we'll use the name node as a prefix of everything that relates to a struct node. We'll basically say, what is the offset between the member V and the beginning of a struct node? This is, the number, the integer that is reflecting the number of bytes between the beginning of a struct node and the first member called V of a struct node. What do you think that number should be?
0.
0. It's 0 because V is the first member of the entire structure, and therefore the address of V is the same as the address of the entire structure. So there's an offset of 0 between the beginning of the structure and where we can find V as a member. Okay, so that's a 0. Then we have to say, okay, what about P next? Where am I supposed to find P next? It's 1 because TTP is a 8-bit architecture, so the address is only 1 byte wide, and it doesn't buy you anything to allocate more space because every single memory read can only read 1 byte at a time. So that whole trick that we used earlier in the C code, that the 64-bit architecture, does not work here at all. So we'll just make it 1. But instead of calling that 1, I'm going to use this technique again. In other words, it is relative to the previous member. We just have to add the size of the previous member to the offset of the previous member. So this way, if I later on choose and go like, I want a new member X before V, then it wouldn't impact anything from this point on, because everything is relative. So we need one more definition, which is the size of a node. So we basically say, what is node underscore size? And how do you think I should define this? How many bytes is a node, and how should I define that? We know the last member is a P next. Do we know the size of a P next? It's 1. So it is 2, but the way I'm gonna do this calculation is it is the offset to the last member of the entire structure plus the size of the last member of the entire structure. So this is a really long way to say 2, okay? But this makes the code more flexible. So later on, if I need to change and say, I want to add a new member and stuff like that, I have fewer lines that I need to change. It's not like I don't have to change anything, it's just fewer lines. So I'm really just trying to isolate changes, isolate the code from changes in the future. Are we doing okay so far? This is the definition of the structure in assembly, okay? Because you simply do not have the language structure to deal with this. All right, so with this in mind, we can now start to write the actual code, okay? So we have a no op, set up the stack pointer like usual. And then we have to push the return address and then call main. So we'll go ahead and do an LDIA with .6+. And then do a decrement D, STDA, JMPI to main, and then when main returns, we're gonna halt. Yep.
So lines 3 to 7 in the C code is the same as lines 1 to 3 on the assembly code?
Yes, that is correct. Line 3 to line 7 in the C++ code is equivalent to line 1 to 3 in the assembly code. All right, so line 5 to line 11 in the assembly code is simply the code that you normally do not see in the C program that calls the main function. And now we need to write the main function. And since main is a regular function, it is really helpful to write the terminating or the return code first. I mean, this is just something that I do because I tend to forget to write this code at the end. So I want to write it first. Okay, now we got a hot mess of things that we need to declare. And we, in all the previous programs, okay, we only have like one, at the most, two local variables where I can just, eyeball and count the number of bytes that I need. Both for allocation, because we typically did in the previous program, I did a decrement D to allocate for the local variables, and then do an increment D to deallocate the local variables. In this case, it is a hot mess, okay, because we do have a bunch of stuff. So instead of doing that, I'm going to do something a little bit different. So I'm going to say, okay, let's look at the local variable R, which is the array. I'm going to call this the local variable that is going to occupy the lowest portion of the frame. So that's why it has an offset of 0 from where the stack pointer points to. And then the next thing is going to be local variable I, which is where I can find the offset to find R and the size of R, which is 4. And then the next one is going to be Pn, okay? So Pn is after I, and I as a unsigned integer with an 8-bit architecture is only going to take up 1 byte, like so. And then this time, I'm also going to have local variable size. LVS stands for local variable size, which is basically keeping count on what is the total number of bytes I should allocate for all the local variables. So let me just kind of pause here and make sure that we understand what each label is trying to represent and how we come up with the definition of that label. Are we doing okay so far? Lines 14 to 16 are representing offsets, the number of bytes between the local variable and where the stack pointer points to after I adjust the stack pointer to allocate for the local variables. Line 17 is trying to figure out how many bytes together do I need to allocate for all of the local variables. Is that okay? Okay. All right. So label definitions do not do anything at runtime. In other words, line 14 to line 17 actually does not do any allocation. It does not do any deallocation. All it does is to define a bunch of constants that are only visible to the assembler. By the time you run the code, it's like, okay, if you don't do anything with the label, it has no impact whatsoever at runtime. So that means we have to utilize these label definitions to actually do something, such as allocating for the bytes for the local variables, and then later on to deallocate those very same bytes. So in this case, since I already know the number of bytes, I'm not going to use increment and decrement D. Yeah, instead, I'm going to have to use something a little bit more generic. So I'm going to do an LDI. Let's use register. I don't care. B is fine. Okay. So let's do this with LVS, the local variable size. And then this time I will subtract that much from the stack pointer. This is for allocating for the local variables that are auto. And then in my very same style, I will do the same thing at the end, load B with LVS. And this time I'm going to add that much to the stack pointer to deallocate these local variables. Are we doing okay so far at this point? So instead of using decrement D to allocate 1 byte at a time for the local variables, I just have to calculate how many bytes do I need to allocate for every single local variable that is auto, and then just allocate all at the same time. It's okay, no problem. You all do that once in a while. But getting back to this, are we doing okay so far? With line 18 and 19 allocating for all the bytes for the local variables, and with line 21 and line 22 doing the exact opposite, which is to deallocate those bytes from the stack. Yes.
So
So my understanding of the labels,
Mhm.
and so you have the name of the label, main LBS, then you have the colon, and then you have another variable label, main underscore P and 1+. So that's how much space is allocated? That's how many
Yes.
bytes here.
Yep, this becomes the number of bytes of all the local variables. Because Pn is the last local variable that I'm allocating for, and it has it itself is 1 byte long. So this is the offset from where the stack pointer points to, and to find Pn, this is the size of Pn itself. So the sum between these two becomes the total number of bytes that I need to allocate for all the local variables. I can draw a picture. I think that will help. So let me do this. There we go. All right, so what is happening here is the stack pointer will be somewhere. I don't really care where it was, okay? So doing this means I'm basically decrementing the stack pointer by a bunch in one single stroke, okay? Now the question is, after we do the allocation, after register D points to this location, where are my local variables? So I need to go back to the code to see, where each thing is. Okay, so it's I, Pn, R, I, and then Pn. Okay, so we have R first. Okay, let me get back to this one. So we have R as the lowest local variable on the stack. It's going to take up 4 bytes. And then we have I as the next one. And then we have Pn as the last one. So R is at an offset of 0 from where the stack pointer points to, and that's why this is 0. I, on the other hand, is at an offset of 4 bytes from where the stack pointer points to, and then Pn is at an offset of 5 bytes from where the stack pointer points to, and then all together, we need to allocate 6 bytes for all the auto local variables. So is this picture kind of explaining things a little better? Okay, yeah.
Is that what 7 of the code on line 7 is for?
Okay, let's go back to line 7 and take a look. Line 7, what do you mean by line 7?
That's a LTI a 6+.
Nope, that has nothing to do with the allocation of local variables. That is just calling main from the entry code for the entire program. Everything related to main starts with line 13, and so far we have only written all the way down to line 25, but we have a whole bunch of stuff that we have to insert in between line 19 and line 21. Yep.
So the main local variable size is storing that picture that you do, basically.
It's storing the 6 of the picture. In other words, I'm counting on the assembler to do the addition for me, so this way I don't make a mistake. And and then I use a label to remember how many bytes I need altogether for all the local variables. So this way I can do one single allocation. I don't do one allocation per local variable, so it saves a lot of code and time. And I can do the same thing, be allocating the local variables. Okay. Any other questions? Okay, the questions? You go like, but Tech, aren't you forgetting 3 other local variables, N1, N2, and N3? I did not forget, okay, because they're not supposed to be on the stack. So that's why, they would not be a part of, the amount of decrement from the stack pointer, nor are they deallocated by adding onto the stack pointer. They have to be allocated somewhere else. And you ask, where somewhere else is? Well, we can just do it here. Okay, this is just a good place as any other place. So N3 is going to be here. And it really is just byte 67, which is in decimal, byte 0. And then we have main N2, which is byte 31, and then byte N3 without the ampersand, because remember, the label is already remembering the address of the next item. So that means main N3 is already the address of byte 67 on line 14. So there's no need to refer to, there's no need to use the address of, because the label is the address. Is that okay? Yep.
It doesn't have to be main underscore N3, just N3.
Oh, you're correct. Yep. The assembler would have a complaint about that too. All right, so we have one more to go, which is N1. N1 has 78 as member V, and then it has the address of N2 as member P next. So that is how we implement lines 11, 12, and 13 of the C code is implemented by line 13 to line 21 in the assembly code. In other words, it's intermingled with the opcodes and everything else. It is statically allocated. It starts to exist as soon as the program is loaded, and it doesn't cease to exist at all, basically. It lives forever. Are we still doing okay so far with that code? Yes.
So it's still in the range, right?
Sorry?
That is still in the RAM, it's not in stack.
Oh, everything is in, yes, it is in the RAM, but not on the stack. Well, we'll find out. Okay, when we assemble the program, the assemble view would actually tell us about the layout of where everything is. So we'll take a look at that one when we get to that one. All right. Are we good so far? Okay, so this is just the how do we allocate, how do we initialize the local variables, in some are static and some are not static. So this tells you the differences between a static versus a non-static, because a static simply means, oh, we'll just allocate those bytes and pre-initialize those bytes, we're done. But if it is non-static, then we have to go through more trouble, because we have to do the actual allocation using code to adjust the stack pointer. And then we have to remember to deallocate those things by also adjusting the stack pointer. All right, so now that we have done all of this stuff, we can now start to actually write the code starting on line 18. Okay, so 18 is a for loop, and someone's going to say, but Jack, you never said anything about for loops and how to implement it. You only said something about while loops. Well, that is true, okay? But a while loop, excuse me, the other way around, a for loop is nothing more than a glorified while loop. You basically have the initialization that needs to go before the loop, and then the post operation to be at the end of the body of the loop. So there are always ways to translate a for loop back into a while loop. So for the most part, a for loop is eye candy. That's basically what it is. All right, so we'll go ahead and implement the for loop, which starts with the initialization of local variable I to 0. So I'm really hoping that at this point, you guys go like, oh yeah, we know how to do that. Okay, we load A with the offset to I, like so. Add AD, adding the stack pointer to the offset. So now register A has the address of local variable I. And then we just have to LDI B with 0, which is the right-hand side. Store register B to where register A is pointing to, because register A has the address of I. So this will initialize I as a local variable to 0. Next, we have to initialize Pn as a local variable to the address of N1, but remember N1 is a static local variable. So the way we do that is very similar. Okay, so there's the P next here. Add AD again. Oh, Pn, not P next. There we go. And then we do an LDIB, this time not with 0, but with just N1. N1, the label, is the address of N1, the structure. Yes.
Yeah, isn't it main N1?
Main N1, that is correct. I keep forgetting to prefix the whole thing with the name of the subroutine. Thank you. Okay, and then SDAB. Okay, so that's the initialization. The loop is going to start here. Okay, so we'll say for begin. Since we only have one for loop, I don't need to use any type of a numerical value to distinguish the loops. And since it's a loop, that it definitely has an and. So the and label is, we definitely need the and label, might as well put it here already. All right, so now we have to put in the code to say, when do we stay in the loop? Well, we stay in the loop as long as Pn is not zero. Okay, this is basically just a shorthand of Pn does not equal to zero. So we'll just have to do the usual trick that we do. Okay, the LDIA with main Pn, add AD. And I'm just looking at the code of what we need to do. Okay, so I'm going to do a little bit of optimization here. So after the LD instruction, register B is going to be the value of Pn, which itself is the address of something. Okay, or no. And then we will do the usual trick of AND BB. Remember AND BB, all it does is to force the content of register B through the ALU so that it would influence the two flags that it would influence. One is the sign flag, which is useless in this case, and the other one is the Z flag, which is useful in this case, because we want to see if register B, which is now the value of Pn, is null or not. So we have the JZI, okay? So now the question is, well, if it is null, are we exiting the loop or are we not exiting the loop? According to the context in the C code, when Pn is null, yes, we are supposed to get out of the loop. So that means we can now go to for end. And we also know that we have an unconditional jump that is needed here to go back to for begin, because that's what loops do, right? You know, at the end of the body, you're supposed to go all the way back to recheck the condition to see whether you need another iteration. So in terms of the C code, we are now done with the condition, and now we can specify what is in the loop itself, which is a little bit of code down there. So we'll go ahead and scroll down in the C code to find out what exactly is in the C code. Okay. All right, we only got line 20. Okay, line 20 is the only line in the C code. The post operation, I'm not too worried at this point. I'm going to deal with line 20 first, and then we'll go back to deal with the post operation. It's called the post operation for a reason, because we don't do that until we are done with the body of the for loop. Are there any questions before we proceed to deal with line 20? Okay, so you look at line 20, and I'm going to do the usual thing, which is handling the right-hand side first, okay, because it looks kind of nasty. So we'll deal with the nasty stuff first. So what exactly is the right-hand side of line 20? What is it referring to? And someone, yeah.
The right-hand side of line is getting the V. So in the top, the structure has two different items. It has the unsigned integer, 8-bit integer value of B, and then the structure node integer to whatever next is. So in line 20, that is calling back whatever value of B is for that particular item.
Okay, so I have a very structured way to refer to these things. So the right-hand side of line 20 is the value of member B of the structure that Pn is pointing to. I know how convoluted it sounds like, but once you get used to it, you know, it's going to sink in a little bit better. Yes. The right-hand side of the assignment on line 20 refers to the value of member B of the structure that Pn points to. That is supposed to be coming from CISP310. So this really should not come as a surprise. I mean, the left-hand side, okay, the right-hand side, yes, that's the content of this class. The left-hand side is content from CISP310. Okay. All right. So how do we get that? What is the first thing that we need to do? What is the ordering of doing things in order to get to the right-hand side of line 20? What do you think? What do we need to worry about first? Yes.
Accessing Pn.
Get to PN first. Yeah, I think getting to PN is important. So let me check back to the registers that are already set up here. So it looks like PN is already in register B. Right? So that means I can now say, okay, that's a register B. And so I'll just comment here and say register B already has the content of PN as a local variable. Well, that saves me a little bit of time. What else do I need to do? PN or register B is pointing to the beginning of a structure. Yes,
O, B, E.
not yet. Okay, there's no guarantee. Now, I know you guys know that V is the first member, and as a result, B is also the address of V. Okay, but you don't want to count on it. Okay, so basically, what you want to do is to say, if V is just a general member of a structure, do I know where to find that member if I know where to find the beginning of the structure itself? Let me repeat that question. Do I know where to find the beginning of a member in a structure if I know the beginning of the entire structure itself? Yes.
Yeah, we set up the offsets at the top of the program as locals.
Yep, exactly. So what we'll do is we're going to use another register, let's say C, and we'll put node underscore V, which is the name of the member that we are trying to access. So register C now contains the number of bytes between member V of the structure and the beginning of the entire structure. So to get to the address of member V, you just have to add, right? You just have to add where the structure is and the number of bytes between the beginning of the structure and the beginning of the member that we want to access. So that means I just need an add instruction here. And which way you add really does not matter in this case. So I'm going to do an add BC. So that means by the time we are done with this, register B is going to be the address of PN points to B. And if you want me to spell out this in English, I can do so. It is the address of member V of the structure that PN points to. Is that okay? Now you probably understand why natural language is not a very good programming language. Okay, some of you are getting that, but some of you are going like, but I still like to use natural language to describe my program. Okay, so we got to this already on line 49. There's no ampersand here. So what do we need to do? Yep, just a load. Okay, so I'm ready to destroy register B. So we'll just do a LDBB. So B is now PN points to B. All right, we finally got the right-hand side. Now it's time to work on the left-hand side. Okay. So you go look at the left-hand side and go like, oh, that's a pretty complex thing. We don't know how to do this. Sure we do. First of all, we need to get to R, right? Where is the beginning of the entire array? Let's get to that first. So we need to find that. And I can reuse registers C at least at this point. So we'll do that. LDI register C with, what is it? Main underscore R at CD. So this will make register C the same thing as the address of R itself. Okay, great. We now know where the entire array starts. So now we also need to know what I is, right? Because I is the index into the array. So we'll get I into a different register. So we'll do LDI. I'm just thinking, do I need register A back? Yeah, I sort of want register A back. Well, okay, that's not optimized. We'll just reuse registers here and worry about reloading something into the register later on. Okay, so we get to this. So now register A is the address of local variable I. Are we good so far? So this kind of code, this template, okay, loading the offset into a register and then adding the stack pointer to the offset should now be a pattern that you recognize just like that. It's like, oh, okay, this is how we calculate the address of something that lives in a frame. What is a frame? The frame refers to a chunk of memory spaces on the stack where all your arguments will be part of that, the return address will be part of that, and then all your local variables will also be a part of that. The key is they are all relative to where the stack pointer points to. If you ask me, so exactly which location is that big, I cannot tell you, because it all depends on where the stack pointer points to at that point of the execution of the program. Okay, so now what do we do? Well, it looks like we're going to need the value of I. Okay, so we'll put that into a register. Okay, so we'll load it into register B. So B is now the actual value of I. All right, so now what do we do? Yep.
We store.
We cannot store yet. We need to not increment. We know where the array is. Okay, we know where the starting point of the entire array is. We know which element we want to access within the array. So how do we get to the address of the element that we want to get to? Yep.
Don't we need to leave B since it's still storing our value from earlier?
I can always reload it later. I'm not sure what you mean.
B has PN. Area B.
B is storing.
Oh, B is the right-hand side. Yes, so B is the right-hand side and, oh, okay, fine. We have to preserve B. So I can only use register A and register C. Thank you. All right. All right, so register A now has the value of I. All right, so what we'll do is we're going to switch back to the picture because I think this will help you understand where the things are, okay? This is element 0 of R. This is element 1 of R. This is element 2, and this is element 3 of R. Does that make sense? Does it make sense that they're in this particular order? Does it make sense that they're contiguous? Okay, so what I is basically the index into the array, which means it's telling me which one of these four do I want to access. What is in register C at this point is this address here, which is the address of the entire array. I know what I is, I know what the beginning of the entire array is. So the only thing I need to know is how big is one element in the array. Because if each element has 4 bytes, I need to multiply I by 4, and that product becomes the number of bytes between the beginning of the array and the element that I need to access. But what is the width of one 8-bit unsigned integer in number of bytes? It's just 1 byte. So multiplication by 1 doesn't do a single thing. So that means in the code, all we really need to do at this point is to add. So we are adding register A to register C. So now register C becomes the address of ARR bracket I, like so.
Adding 0, so that doesn't really change anything right now.
I'm not adding 0. There's no guarantee of what the value of I is. I mean, yes, for the first iteration, it should be 0, but for all the subsequent iterations, it may not be 0 anymore. All right. So I think we're ready to go because now we have the address of the left-hand side. You go like, what about the plus plus? I can deal with that later. Okay, we'll deal with the plus plus later. We'll just kind of focus on getting this part done. So now we do STCB, and that will do the assignment. And now I have the post increment to deal with, which means I have to, since I ran out of registers, okay? So this is the problem with only 4 registers and one has to be served as the stack pointer. I ran out of registers. So now I have no way but to recalculate the address of I, so I can increment it. It's not too big of a problem, okay? So we just have to do another LDI. Technically speaking, I can shortcut just a little bit, but I'm not gonna shortcut it. So I'll just LDI, LDIA with main underscore I, add AD, LDBA, increment B, STAB, and that will do the I++. Okay, so let's take a look at this one and find out exactly what it's doing. A is the offset to local variable I. A is the address of I. B is the value of I. B is the value of I+1. Oops. Ah. There we go. And now we're going to store it back to A. So basically, this is saying A gets, oops, take it back. This is I gets I+1, which is I++. So with these programs, it is important that you track what is in each register at any specific time. Okay, and relate that to the C code, because you can see how I'm not just saying, oh, A is the sum between register A and register D. That doesn't tell me a single thing. It's useless. That comment would have been useless. But instead, I say, oh, register A now has the address of local variable I. That is helpful, because now I see how the assembly code is corresponding to the C code. So that is the one thing that you need to do with all the sample programs that I have written up to this point. Now you may say, but Ted, but you gave me the program, you have these comments already. I can strip the comments so that you can go through this exercise as you read the code. Okay, so if that is something that you want me to do, it's not a problem. Question?
Is this all like?
Yes, this is all line 20. So line 20 is technically from line 48 to line 62. Aren't you guys starting to appreciate the C compiler?
Pretty nice.
Yes.
So how would you shortcut it?
Shortcutting it?
That last, the posting grid.
Okay, so I can shortcut it just a little bit because I already have the value of I in register A. So I can reuse that instead of loading it into register B. But I do have to, kind of change things a little bit. These three would have to be register B, but register A already has the value of I, so I can just increment A and it's going to be back to where it's supposed to go. So in other words, I don't need to read I again from memory because I already have it in front of the registers. But that's kind of messy, because people actually have to maintain a lot more than this code here, because this code basically says, we'll just redo everything from here. So it does not strain a person as much to read it. Any other questions? Okay, we got one more thing to do. So we have the post operation, which is Pn gets Pn points to next. Okay, that's one post operation that we also have to do at this point of the program on line 64. So how do we do that? Okay. This is the value of P next as a member of the structure that Pn is pointing to, and we're using that to update Pn itself, which is a local variable. So once again, the right-hand side is a little bit messier than the left-hand side. We'll deal with the right-hand side first. What do you think of this? What do you think of this particular expression? Do you think we can just kind of copy and paste a bunch of code? Because I think we have done this already. Okay. So the way we're going to do this is to say, let's get to Pn first. So LDIA main Pn. This is the offset to local variable Pn. At AD, this is the address of Pn. This time I might want to keep it around if I can, because I'll need it, because it is also the left-hand side. So it would be kind of nice if I can keep it around. But for the time being, I need to dereference it too. So I'm gonna dereference it into B. And even I really cannot remember which register has what. So I'm gonna have to track it myself too. So now B is PN, which is supposedly the beginning of a structure. But I'm not interested in the entire structure. I'm only interested in the member that is called P next. So that means I have to get to member P next, but I know where the structure is already. So I just have to add the offset between the beginning of a structure and the member P next to the address of the structure, which is already in register B at this point. So we do LDIC with node underscore P next. Okay, this is the offset from the beginning of a structure to the member P next here. And then we have to add this to register B. There we go. So register B is now the address of member P next of the structure the PN points to. And one more dereference, we'll get to the value of the member itself. So LDBB. So now B is PN points to P next, which is our right-hand side. So now we already have the left-hand side in register A, because register A still maintains the address of PN, which is our local variable. So we are now ready for the ST instruction. So STAB would finish line, well, the post operation specified on line 18. If you don't get everything the first time, it is okay, but you kind of need to focus on the general concept of how structures work. Yes.
So is ampersand PN arrow P next, would that be equivalent to just PN dot P next?
No, you cannot put a dot. So the pointer thing cannot be replaced by a dot because the dot means the left-hand side of the dot has to be the structure, not the address of the structure.
Oh, okay.
Yeah. So that's why C and Java are different in a major way because Java has no pointers. So that's why people who use Java to satisfy the prerequisite of this class might have a little bit more struggle because they are not used to the concept of pointers. Are we still doing okay so far with this? All right. So I think this code is done, except for the return 0 after the for loop. That's an easy thing to do. LDIA with a 0, easy peasy. And I think we're all done. All right, so before I switch, run the C code, find out what is in R in C code, and then do the same thing in assembly code to double check and make sure the assembly code has the same thing. Do we have any other questions about this code? And if you remind me, I will definitely upload this to the announcements so that you guys can have both the C code and also the assembly. We good so far? All right. Okay, so let's go ahead and run the code in C first. GDB LL, because it's already compiled. And we'll put a breakpoint on line 22, which is right after the entire loop. Run the code and say print what is in R. It is very obscure. It says n\037C. Is that correct? Well, let's find out. What is the ASCII code of n? The ASCII. Yes. You can probably just say ask for that too. So that's the V of the first node, right? N1. What about the \037? That is octo 37. So octo 37 is 3 times 8 plus the 7. That's base conversion stuff all the way back from what, week 3 or so? That's a 31. And then the ASCII code of C is 67. So we got the 3 values back from node N1, N2, and N3. Is that okay? All right. So now we want to run it in assembly code. And since we are sort of running short on time, I'm going to cheat and use River Spider. So we'll switch to River Spider, and that is in a different folder. And the program is called ll.ttpasm. Object code is good, simulation done. All right, so now we can switch back to the browser, go into the assembler. Okay, so the first thing we need to do, there are a few really important things that we need to do here. The first one is to go to the assemble view to find out how things are laid out. Okay, the first part is not surprising. Now, one part may be surprising is the definition of the structure did not end up using a single byte, because that is all about the definition of the labels, and definition of labels do not use any bytes in memory. And then we have the entry code, which is from this line to this line over here. And then we have the definition of the 3 static local variables. So you can see the static local variables are basically using location A, location B, location C, location D, location E, and location F. They're not a part of the stack. The main program is starting at location 10 in hexadecimal, and then it ends all the way down here at location 4B. That would be main. All right. So how do we check whether this program worked or not? Let's go back. Sorry?
Does it return back to the alt?
That would be a good thing to check, but I also want to check whether it did the right thing and put the right values into R, the array. So getting back to this picture, we know that there's nothing that we need to worry about except for return address here, because remember, main is treated as a normal subroutine. So we do have a return address associated with main, but main has no arguments, it has no parameters. So that means this location here is location FF. This would be location FE, FD, FC, FB, FA, and F9. Are we doing okay so far? Because what I want to do is to figure out what I should be looking for in the trace. Okay, what location should be updated to what? So we know that F9 is supposed to update to what in the C code? Do you guys remember? It is the ASCII code of N, which is what, 60, 71, I think? 78, okay. So 78 is decimal, and we need to translate that into octal, in hexadecimal. So 4 is 64, is 71 again? 78, so we have a 14, which is an E. So it's 4E over here. This is 31, which is a 1F. And this one is what, 69, I think? 69. Sure. Which is a 4-5, because 4 times 16 is 64, and then plus the 5 would make it 69. Okay. Sorry?
It's 67.
Was it 67? Okay, I cannot remember details. I cannot remember details of my own programs. Okay, we'll double check that wrong directory. All right, so we have 60, 79, 31, 67. So that means, in the code here, this is supposed to be what? I cannot remember, I have to look again. 67, so it's a 3, so it's a 4, 3 over here. All right, so what we're looking for, oh, you guys cannot see it. Hold on a second, there we go. So what we're looking for is location F9 to get 4E, location FA to get 1F, and the location FE to be 4-3. Those are the things that we're looking for. So now we switch to, the program has run already. It's just a matter of time to go to the analysis tab to find out what happened to those 3 locations. So I can highlight the entire column of the update of RAM locations. and then go to edit, find and replace. And this is why regular expression is really helpful because I can look for all three at the same time. So it'd be the asterisk F, and then the range that we are looking for is, okay, let me show you the picture first so that you know what I'm talking about. So we are looking for location FAB here. So when we switch back to the browser, we can now specify exactly that 9AB, because that specifies what that one character can be. We have three choices here, and then press the equal to, and then we go find. Okay, so location F9 is a 4E, location F8 is a 1F, and location FB is a 4-3. So they all worked as expected, and we scroll down and we do end up at the halt instruction, which is good. So this trace is important, okay? Because I can show you the picture, right? The picture that I showed you earlier, which is this one. I can show you this picture, but how did it become like that? That's the question. How do I change the stack pointer? How does it get moved around? How do we access, the nodes, okay, the various things in the node? I said that I would get to the pointer first, and then we add the offset between the beginning of the structure to the member of the structure. I mentioned all of those things. So did it stick in your mind? Okay, some of you not, okay, I'm not talking to you guys. Are you talking to those where they go like, okay? So it does happen, okay? But that's why the trace is important, because the trace shows you step by step, frame by frame, what actually happened. So when you combine that, okay, once you comment your program and you combine that into, because you can read your own comment here, then you can actually get to see dynamically when the program runs instruction by instruction, what gets calculated when and how we get it done. That is how we study for this class. That and also writing your own code in the homework assignment. And some of you may say, my homework assignment didn't work. I have to spend like 4 hours to do it. Every single time you find a bug in your program, that is learning. If you get the program working the first time, I am sorry. Because you're not learning as much as those people who got like, oh man, there's another mistake. My program didn't run again. How do I fix this? Why is it not running? The why is it not running is the most crucial part of learning in this class. All right, so I will give you guys the access code of tonight's lab. It's not big, okay? The lab itself is not really that big.
Yeah.
It's called recursive call, and the access code is FIB, F-I-B. It is the short form of Fibonacci, okay, not Ryan. All right, I'll see you guys in the lab, and I'm suspecting by the time I get to the lab, 25% of the class will be engaged. This one, lab, but not the program.
Okay, yeah, obviously, otherwise you're not giving us till 5 more to do it.
Be the fourth, you.
Ah.
Yes.
We can only go.
So, I'll take that.
Yeah.
Magic